Bitcoin is brand new to mankind in that it's both a currency and a payment network simultaneously. And this is where Bitcoin gets its value. The immense network of computers all around the world running the Bitcoin distributed ledger. Every second of every day, these computers are keeping the ledger updated and in full consensus via a system that incentivizes them to process and confirm transactions. The system that Bitcoin runs on is called blockchain. Think of it as a modern version of an old-fashioned bookkeeping ledger, but instead of a handwritten list of entries and calculations, a blockchain is a digital list of entries and calculations. A block is simply a bundle of transactions. Think of a block as a whole page of transactions in the old-fashioned ledger. A blockchain is just a chain of blocks. It's the same as a whole series of pages in the old-fashioned ledger. Easy, huh? Here's how it works. The Bitcoin blockchain actually exists in every one of the millions of computers on the network as exact copies of each other. However, for this example, so that we can zoom in and you can really see just how a blockchain works, I'm going to show it as one giant blockchain in the middle of a small network of computers. Let's follow a pizza transaction with Bitcoin. When the transaction occurs, it first appears on the network in a pool of unconfirmed transactions, along with thousands of others from all around the world. Millions of different computers from the network then gather some of these transactions and place them in their own blocks. The computers are all creating blocks constantly in the hope that theirs will be the next one added to the official chain. A new block is added to the chain every 10 minutes or so, when one of the computers wins the right to have its block recognized as the next in the chain and is rewarded with a prize of newly created bitcoins. The way a computer wins the prize is by trying to guess the answer to an extremely difficult math problem. In fact, the problem is so difficult that even with millions of computers making guesses billions or even trillions of times per second, it still takes roughly 10 minutes to find the answer. Once one of the computers guesses the correct answer and wins, all of the millions of computers on the network that did not win are instructed to throw away all the work they have done, update their ledgers with the block from the winning computer, and start again with a new math problem. In doing so, the computers use an immense amount of power and cost a literal fortune to run. So why do they do it? Because it can be very profitable. This is where the term mining for bitcoins comes from. Instead of striking gold by mining for precious metals in the wilderness, these computers are hoping to strike Bitcoin by mining precious numbers on the blockchain. But when these millions of computers are selecting transactions to go into their blocks, they aren't all selecting the same transactions, and not all the blocks are the same size. Some contain more transactions, some contain less. When blocks are thrown away, the transactions they contain go back into the pool of unconfirmed transactions. This means that the probability of a transaction being confirmed and staying in the order it was confirmed in is not absolute, but it becomes more of a certainty every 10 minutes as new blocks are added. In fact, for very large transactions, it's suggested that you wait for 6 or more blocks, about 60 minutes, to be absolutely certain that a payment is permanent. So why is it so slow? Why is your pizza cold before you own it? Interestingly, the system is slowed down on purpose, and here's why. With the insane difficulty of guessing the answer to the math problem, you would think that the odds of 2 or more computers winning at the same time are extremely improbable, but it actually happens quite often. This is called a soft fork, and when it occurs, all the computers in the network receive both of the winning blocks and are instructed to create a new block that will chain to the block they received first. But because of varying internet connection speeds, different computers receive different winning blocks at different times. The tie is broken roughly 10 minutes later when one of the computers solves the new math problem and its block is added to the ledger, and the longest chain wins. But what happens to all of the blocks on the other side of the fork? They're discarded, along with all the transactions they contained, which go back into the pool of unconfirmed transactions. This soft forking is the main reason the system must be slowed down on purpose via the math problem. If the system was instant, it would be forking everywhere, all the time, and there would be no consensus. no one would have any idea of which ledger was the correct one, and every computer would be busy building a different block to create yet another fork. The slowness and immense amount of computing power is required to keep the Bitcoin ledger in full consensus. Therefore, as more and more computing power is added to the network, the system automatically adjusts to increase the difficulty of solving the math problem, which then requires even more power. If Bitcoin is ever going to be widely used, it will be using a massive amount of the world's energy. There are other systems for reaching consensus, but we'll look at those later in the episode. For now, Bitcoin is working as intended and allows people to transact with each other using the internet anywhere on Earth. Bitcoin, it's the first full consensus distributed ledger that mankind has ever seen. Since the advent of Bitcoin, there have been many thousands of blockchain-based cryptocurrencies created, and now there are more of them being created every single day. So what's different about HashGraph? Well, it isn't blockchain. It's totally different. In fact, the way it works is a real mind-bender and not very easy for me to explain, but I'm going to give it a try. Instead of a block in a blockchain, HashGraph calls their packages of information events. Your computer takes a transaction like a payment, or anything else for that matter, such as an action in a video game, an offer to sell merchandise or even sell stocks or bonds, a bid on that item, a contract, or even a law. Pretty much any information or transaction you want to record, and it puts it in the event. For transmitting information quickly, HashGraph uses a technology that has been the gold standard in computer science for decades. It's super fast, and it's called Gossip Protocol. Your computer randomly tells another computer in the network about the event you've created, and that computer responds by telling your computer about any events it heard about. Then that computer tells another computer about your event and the other events it heard about, and the computer it's talking to responds by telling all the events it knows about. It's absolutely the best, most efficient way to spread information, and it's exponentially fast. But here's the twist. Each time a computer tells another computer about an event, it also includes the information of the time it heard it and who it heard it from, and the time they heard it and who they heard it from, and so on and so on. It's called Gossip About Gossip, and it lets everyone know what everyone else knows and exactly when they knew it in just fractions of a second. The other major component is an even older technology, and it's the most robust, secure, and certain way of coming to absolute consensus. It's called voting protocol. But until now, it was so slow that nobody ever used it. And the twist that HashGraph has given it is that there's no voting. Instead, because everyone already knows what everyone else knows, you can mathematically calculate with 100% certainty how they would vote. It's virtual voting, and it allows HashGraph to come to consensus almost instantly. So instead of recording things on a block and then adding it to the blockchain once every 10 minutes, HashGraph events are added to the system instantly the moment they're created, so they don't have 10 minutes worth of information in them. This means that they're small and they contain far less data, so they use very little bandwidth and are much easier to transmit. And because it's not trying to guess the answer to an incredibly complex math problem trillions of times per second, HashGraph uses just a minuscule amount of power. From what I've seen so far, compared to blockchain, HashGraph is lightning fast, more secure, and provably fair. All events are time-stamped the moment they're woven into the system, so the record of whose event came first and whose came second is instant, and there's no such thing as soft forking or unconfirmed events. It can also replace huge portions of the internet that are currently run by centralized servers, by replacing them with the shared computing power of all of our own computers, iPads, and cell phones. It looks like HashGraph might just have the potential of fulfilling all the original hopes and dreams I had for blockchain technology. The power to decentralize and remove the middlemen from commerce, banking, stock markets, and much of the legal system and government. With the speed at which this technology is evolving, the future is looking bright, and HashGraph is the perfect example of just how fast things are moving in this field.